Yeah, that was more important, which is now covered in bugs, apparently, I've heard. Yeah. I. Yeah.
But then the like, well, they eat the vegetation or whatever. I was like, okay, bro, but the dirt is really plastic. So that makes zero sense.
I know. Oh, goodness gracious. Here we are again. Welcome back. Today is Wednesday. We have until 10:28 in this class period. There is no extension, obviously. We'll get this thing done. Looks like I have about 6 or so people in the live chat. If you guys would be so kind, 7 now, if you would be so kind to leave a comment in the chat, that would be absolutely wonderful. So I can take an appropriate attendance when the time is appropriate. I'm just bringing open the chat on my phone right now so that I can see all of those comments as they pop up. There they are. See, there you guys are. In front of the camera with all your things. Cool. First thing, let's talk about the end of the year. I'm going to move the camera over to this thing over here. I got to give you the updated information that I got since I saw you last. First, something you already know. Your senior final exams will be taking place on Friday, June 11th. I got confirmation from the other Algebra 2 teachers. For Algebra 2 CP, we will all be taking our final exams during the senior exam week. So just so you are all aware of that, your final exam will take place on Friday, June 11th. That would be the 3A final exam for seniors. So during that week, they are full days of school, so you will go to all 4 class periods during those particular days. So I would see you on that Monday, and I would see you on that Wednesday, but then you take that final exam on that Friday. And then the following week, when there's quote-unquote actual final exams, during that 3A exam, obviously we will not be officially taking the final exam during the that Thursday, June 17th, but I will still have to take an accurate attendance, and the only people that would be excused would be the seniors. So please keep that in mind. On Thursday, June 17th, the date of the 3A exam, obviously we will have already taken our exam. So, Ms. Murky, can I just not show up to school? Well, that's your prerogative, but I would then mark you absent. So please keep that in mind. Okay. Next, on Monday, I said that I was going to assign an edge elastic major to you, and I have. That edge elastic major was assigned yesterday. Let's see. Oh, good. A few people have already done it. Good for them. I haven't checked any of the scores yet. I just see how many people have actually turned it in. But even though I assigned it yesterday and I'm seeing you today, I did not make it due until Friday at 2 p.m. So you do have a bit of time to get that done until Friday at the end of the school day. That is when that thing is due. So please make sure that you are jumping on that. That is the rationals function major. It is via Edge Elastic. Like I said, a couple people have already gotten it done. I'm just going to double check Edge Elastic real quick while I'm thinking about it. Sign in. Period 3A. There it is, in progress. Oh, good. There we go. Yeah. And I can see the couple people who have gotten it done so far. Nice, nice, nice. And yeah, I'll update the scores on Genesis when the time is appropriate because I still have to go through the individual questions. And like if you put in like, X equals 3 and they just wanted 3, they mark it wrong, but then I'd have to go back and mark it right. But we'll do that. Okay. Next, I would like to begin the next part of Algebra 2, which actually happens to be the last part of Algebra 2. Ladies and gentlemen, today I would like to introduce the last main unit that I will be covering in Algebra 2 before the final exam. In order to do that, I do have to introduce it with a little bit of story. There was once a boy named Carl, and believe it or not, this is a true story. Carl was about 8 or 9 years old when he went into school, and there's maybe like an hour or so left in the school day, and the teacher did not feel like doing anything. So the teacher told the class, you need to add up all of the numbers from 1 to 100. And when I say add up all the numbers from 1 to 100, I mean like I want you to do 1 plus 2 plus 3 plus 4 plus 5, all the way up to 100. The teacher did not feel like doing work that day. He gave the assignment to the class as busy work, and he told them that you better do it because it will be worth a large part of your grade. They did not have calculators. They did not have electronics. And they set off on their task while the teacher sat at his desk. Of course, when you were done, you were to turn in your answer. What is the answer? Well, young Carl took about 30 seconds, and he delivered the correct answer to the teacher. The rest of the students took pretty much the full hour because they were doing this all by hand. No electronics, no computers. They didn't have any of that. But young Carl delivered the correct answer within 30 seconds. Now, I am not going to have you sit and actually try that example, but I'm going to tell you what the correct answer is. The correct answer is 5,050. My question to you is, how did he figure it out in 30 seconds? He did not know the answer beforehand. He did not cheat. As an 8 or 9-year-old boy, he did it in his head. No. He is not one of those weird geniuses that can literally compute numbers in his head super fast like that. He can't do that. He used a very logical, straightforward approach to be able to get such an answer in such a short amount of time. So I ask you to think, how did young Carl figure it out? It's more of a rhetorical thing. I am going to show you how he did it in his head in such a short amount of time. Now, here's the thing between Carl and all the other students. All the other students, when they turned in their work, they wrote out a bunch of stuff. They had all this scratch work written on the side. On Carl's paper, when he turned it in, it had no work whatsoever. It only had the number 5,050, which was the correct answer. Well, I'll tell you something about Carl. Carl ended up growing up to be one of the greatest mathematicians in recorded history. No. I didn't say he wasn't a genius. I said that he wasn't one of those computational geniuses. Like, have you ever seen like like on a TV show, like somebody who's supposed to be like a computational genius and you say, hey, what's the square root of 2? And they could round off the square root of 2 like to 20 digits long. Yeah, Carl couldn't do that. Yeah, he couldn't do that at all. You know, I don't know who that is. Who's Spencer Reed? Okay, can he do that? Yeah, Carl couldn't do that. Yeah, it's a different type of genius. It's like, do you know the movie Rain Man? It was Dustin Hoffman and Tom Cruise from the 1980s. He was basically like he had like some kind of learning disability that allowed him to be like a computational genius to be able to cheat at gambling. Anyway, Carl didn't do anything special. He figured it out in his head. I want to show you how. See, when people typically add up numbers, when you guys are first taught how to like add up numbers, aren't you taught how to add up numbers like this, where you're like, okay, like 52 plus 41, you add the ones and then you add the tens. You're taught how to do that like in elementary school. That's not how Carl thought about it. Carl thought about it as, well, imagine for a moment, visually imagine that all of these numbers are written out left to right. Instead of vertical, imagine them horizontal. Now, take the number 99 and move it under the 1. Take the number 98 and move it under the 2. Take the number 97 and move it under the 3. And he did that all the way in his head, mind you. He did that all the way up to the number 49, where underneath the 48, he put a 52, and underneath the 49, he put a 51. What's so special about all those pairs of numbers? Okay, they all add up to 100. How many pairs did I just get 100 with? How many pairs did I get of 100? Not exactly 50. There will be 50, but technically I have 49 pairs. It's like there's a pair here, a pair here, a pair here, a pair here, and a pair here, all the way down from 1 to 49. Is that fair? Okay, there are 49 pairs of 100. That's why I'm being very specific with the word pairs. There are 49 pairs of 100, which you could easily calculate in your head. But then I ask you, what are the only two numbers you haven't used? There are two numbers that you haven't used. 100 and 50, which he added up in his head, wrote it on the piece of paper, walked up to the teacher's desk, and said it there. Clear? In his head. He visually saw the numbers 1 to 100 in his head. He took the second half of those numbers from 51 to 49 and inverted them underneath the 1 to, from 51 to 99, inverted them underneath the 1 to 49, 49 pairs of 100, and then, oh, there's only two numbers I haven't used. The teacher thought he cheated. Carl had no work to back it up. He tried to explain, but the teacher didn't want to hear it, and he got in trouble. Poor Carl. Eventually, when Carl Gauss was older, eventually when he was a grown-up, he was able to devise formulas for determining the sums of such a question, no matter what number you start with, and no matter what the pattern actually was. This is a true story, though. You can look it up. Carl Gauss, Gauss. Well, one of the most famous mathematicians of the 1800s, probably the world's last pure mathematician, meaning that he covered almost every known subject of mathematics at that time. Today, they're more specialized. It's weird. We are going to be spending some time with numbers that have patterns, a list of numbers that have patterns. Just like the one that he did. He was able to devise, based on that list of numbers, some kind of routine in order to get the summation of them. And now I am going to be introducing you to sequences and series. Ladies and gentlemen, if you do not already have them out, I'm going to need those notebooks out and open. I have various examples to kind of walk you through this today. And I do have a not fair challenge. A not fair challenge. And when I say it's a not fair challenge, I mean that in all the years that I've been showing this not fair challenge to Algebra 2 students, not one of them has been able to get the exact right answer without cheating. And when I say without cheating, I mean like looking it up online. But we'll get to that not fair challenge in a little bit. First, let's talk about what I'm going to be labeling this whole thing as. Today is May 19th, and I am calling this Intro to Sequences/Series. And like I said, this is the last major chapter that I will be covering in Algebra 2. Let me start off with a very basic definition. A sequence is a list of numbers with a pattern. A sequence is a list of numbers with a pattern. A lot of the time you can identify what that pattern actually actually is just by looking at it and thinking about it for a few seconds? Yeah, absolutely. Yes, you can. But then what we do with that pattern, what we do with that information, will eventually be the questions that we are faced with later on in this chapter. If you know the pattern, if you know what the pattern is, you can guess the next number. Now, knowing what the pattern is not necessarily what the question will be asking. But knowing what the pattern is a huge step towards solving whatever the question is. Yep. So here are just some very basic examples that I can show you. They're going to get obviously more interesting the more examples that I put down there. Let me start off with something very simple, something that basically Carl Gauss started off with. 1, 2, 3, 4, 5. ... This is a list of numbers with a pattern. That's technically what it is. And this will be the hardest question that you're ever faced with in your entire life. What's the next number? Oh, come on, you can do it. What's the next number in this list? We did it! Yay! Okay, so yeah, it's like, come on, we all know that. Mr. Archie, what's the big deal with knowing that it's a 6? I know, but it's a pattern. The pattern is that you add 1 every time to get to the next number. Yes. There are multiple ways of describing it, but yes, it's a list of numbers with a pattern. Let me give you a different list, one that is not as obvious. Here's a different list. Dot. Now, if you know what the pattern is, you should be able to tell me what the next number is. So I look at this and I see 1, 3, 7, 15, 31. What's the next number? Like I said, this one's not as straightforward obvious. It is 63. How did you get it? Ah, interesting. That's one way of describing it. Let me say exactly what you just said for the people online and for the people who didn't hear you. He said the next number is 63, and I absolutely agree. It is 63. I said, how did you get it? And he said, double and add 1. And what that means is, well, you take the first number. If you double it and add 1, you get 3. If you double 3 and add 1, you get 7. If you double 7 and add, I said add 3, didn't I? I said add, yeah. Double it and add 1 is the pattern every time. Double it and add 1, double it and add 1, double it and add 1. 31 times 2 is 62, plus 1 is 63. Yay. There's another way of describing that pattern, though. There's a secondary way of describing that pattern besides doubling it and adding 1. What is this? Oh, cool. Basically, what somebody described to me yesterday, which I didn't think about, was, well, look at these two numbers right here. To get from 1 to 3, you have to add 2. And I'm like, yeah, you do have to add 2. And then to get from 3 to 7, you got to add 4. And then from 7 to 15, you got to add 8. Plus 2, plus 4, plus 8, plus 16. He said to me yesterday, logically, the next thing you do is add 32. And I said, yeah, that works as well. Here's another one. 1, 4, 9, 16. ... What's the next number? This one, again, might not be as obvious. But there is a definitive pattern to that list of numbers. What might it be? Or maybe not what the pattern is, but what's the next number? There's two, in my opinion, there's two main ways of describing the pattern. One way of describing the pattern would potentially be finding the difference between each set of numbers. It should be 25. How'd you do it? The difference between here is 3, and then here? Nice, so plus 3, plus 5, plus 7. Logically, the next one would be plus 9. Yes. Here's another way of looking at it, though. 1 squared, 2 squared, 3 squared, 4 squared. Logically, the next one should be 5 squared. We're both correct. We're both correct. It's just a list of numbers with a pattern. Here, I got one more that I'm going to write down. I got one more that I'm going to write down, and then I got one that's not fair. I'm just going to be completely honest. I have one that's just completely not fair. So here's one more that I'm going to write down. This one might be familiar to some people. This one might be familiar to some people. What's the next number in that sequence? This one's not as obvious. Like I said, they do get progressively more difficult as time goes on. Well, don't tell me what you think it is. Don't tell me what you think it is. Tell me what you believe. I'm sorry, let me rephrase. Don't tell me what you think the pattern is. Prove to me you know what it is by telling me what the next number is. 8. It is 8. What you were about to describe to me was this. You were about to describe to me, do you take the two numbers and add them together to get the next number? And the answer is yes. You take the two numbers, add them together. 1 and 2 make 3. 2 and 3 make 5. 3 and 5 make 8. Anyone ever heard of the Fibonacci sequence? Yeah. In discrete math, not algebra 2, but in discrete math, we deep dive the Fibonacci sequence. And when I say we deep dive the Fibonacci sequence, I have a whole unit devoted to the Fibonacci sequence and the divine proportion known as phi. It's amazing, in my opinion. But I can't go into those details now. I have a not fair challenge for you. I have a not fair challenge for you, and I'm going to put it on the board. And I'm going to put it on the board because I don't want you to put it into your notes. I don't want you to put this into your notes. But I have a not fair challenge for you. And if you think you know what the answer is, then you can tell me by telling me what the next number will be. Here's how it starts. Here's how it continues. Every time there is a comma, that is the next number in that particular sequence. That's a 1 right there. I just messed up the marker a little bit. That's my sequence. My question to you, what is the next term? What is the next term? I'll give you a little bit of time to kind of get that done. Here's what you missed. While you're thinking about it, like I said, this is a not fair one because it doesn't use the typical rules of adding, subtracting, multiplying, dividing. It doesn't. It doesn't. I had a professor put this up on the board one day when we were doing series and sequences in number theory. Loved that class. And he basically put it up there and said, no one's been able to solve this without using the internet. It's on the internet. You could easily Google this and get the answer in like 2 seconds. But that's not fair. That's not fair. Don't do that. You can prove to me that you know what's going on by telling me the next term in the sequence. I've had a lot of interesting ideas. What's your guess though? So like oh yeah, no, that's not it. Now I'll tell you, I like when my professor put this up on the board, I'm telling you right now, I didn't get it. I had no idea. We had been studying this stuff, series and sequences, for like a straight month. And he puts this up on the board, and we're all dumbfounded. Because this thing does not follow normal rules. This is a not fair challenge. This is a problem where you really have to think outside the box. But then once you see what the answer is, you're going to go through two emotions. One, oh, that's really cool. And two, oh, that wasn't fair. Those are the two emotions you're going to go through. But this is still a sequence. Because according to the definition, a sequence is a list of numbers with a pattern. I didn't say how that pattern would take place. No. Is it what? No. Here's the thing. I'm going to write the next number up there. But I'm still not going to give away what the pattern is. Because maybe the next number will help you figure out what the next term is. So I'm going to write the next term, or what the pattern is here. Ready? Here's the next number. Wait, read. I'm going to write it over here. Say it again from the beginning. So like 1, 1, 1. No. You ready? That's the next number. Why? Where'd that 3 come from? You ready? Here we go. Here's how you do it. What's that? Oh, thank you for that. So it's, sorry, say it one more time. How many are there? So if you were to tell me how many there are and what it is, you would say that there is... How many ones are here? There are 2 ones. There's 1, 2, and 1, 1. There's 1, 1, 1, 2, and 2 ones. There's 3 ones, 2 2s, and 1 1. I told you it was a not fair challenge. I told you it was a not fair challenge. It did not follow the regular rules of adding, subtracting, multiplying, dividing. It was verbally describing what came next. I know, but I warned you. I tried to warn you. But now, that's besides the point. There are an infinite number of series and sequences that I could throw at you, but I'm not interested in an infinite number of series and sequences. I am interested in 2 main types of series and sequences. And the one that we're going to be focusing on today is known as an arithmetic sequence. An arithmetic sequence. It's the type of sequence that young Carl Gauss looked at. It's the type of sequence that he devoted a large part of his career to and was able to determine formulas that no one before him had been able to do. So let me give you this definition. A sequence, as I've established, is a list of numbers with a pattern. Whereas an arithmetic sequence is a sequence with a common difference. And I'm putting this in parentheses because I'm kind of like redefining what that actually means. You basically add or subtract the same number each time. You add or subtract the same number each time. So in the story of Carl Gauss, he dealt with, 1, 2, 3, 4, 5, 6, all the way up to 100. That was an arithmetic sequence, because to get to the next number, you just have to add 1, add 1, add 1, add 1. That's arithmetic by definition. Here's a very basic example of an arithmetic sequence. Give me a number. Give me a single-digit number. Don't make it 1. Make it anything else. 5. Okay. Give me another single-digit number. Don't make it 1 and don't make it 5. 3. That's all I need. That's all I need to get this thing done. So the numbers that you gave me were 5 and 3. Mr. Markey, where's the 3? Well, hopefully you can figure out where I put the 3. I put a 3 into that problem. I just didn't write it. Joe said 7 in the chat. I'm sorry, Joe. You weren't fast enough. But I put a 3 into it because 3 just so happens to be the common divisor. Now, I'm going to walk you through this, and we're actually going to figure this thing out eventually. But let me give you this and show you the importance. The importance of what I'm about to write down. Put a little wavy box around this. What in the heck is that formula right there? That formula, that equation that I just wrote down, that little black thing is a mess up. But that formula is the formula that governs this entire sequence. How many terms in the sequence did I write down? How many terms did I actually write down in the sequence? I started with 5. Come on, how many terms did I write down? It's a single-digit number. You can take a guess at it and get it right. Yeah, I wrote down 5. I wrote down 5 terms. I wrote down the first 5 terms. Question, if I asked you, what was the 6th term? What would you tell me? Say again? 20. Because you know what the common difference is. You know that it's plus 3, plus 3, plus 3, plus 3. Yes, the 6th term is indeed 20. But check this out. This formula. If I wanted to figure out the 6th term, I could simply plug in a 6 into that equation. 18 plus 2 equals 20. Mr. Argy, what's the big deal? Why can't you just add 3 to get the next term? Yes, of course. If I just asked for the next term, add 3. Why would you bother using a formula? Question. What if I asked you, what is the 600th term? What if I asked you what the 600th term was? Ooh, all of a sudden it's not so easy. I literally, yesterday, I asked this question to somebody, and here's what they tried to do. Obviously, it was different numbers, but here's what they tried to do. They were like, Mr. Margie, look, it's simple. You just do this. Start with 5, and you add 3. That's the 2nd term. 3rd, 4th, 5th, 6th. There's your 6th term. Okay. 7, 8, 9, 10, 11, 12. And they were literally like, no, why would you do that? Why in the world would you do that? You're not going to be hitting that button 600 times. Use the formula. I gave you that formula. Ms. Reggie, where'd the formula come from? I'll tell you in a little bit. I'll tell you exactly where that thing came from. But if you want to find the 600th term, all you would have to do is something like this. Now, by the way, how I would read that, how I would read that is I would read that as A sub 600. Just like I would read this as A sub n. It's a little subscript. But if I want to find the 600th term, all I have to worry about is plugging in that number 600 into the formula. And that gets me 1802. 1802. That's the 600th term. If I legitimately hit enter on that calculator 600 times, then yes, I would eventually get to 1802. Use the formula. Use the formula. Well, how did you get that formula, Mr. Markey? I'll show you exactly how I got that stinking formula. I got that formula through this. This is the general rule of an arithmetic sequence. This is the general rule of an arithmetic sequence. Now remember, an arithmetic sequence is nothing more than adding or subtracting the same number every single time. It adds or subtracts the exact same number every single time. No big deal there. But now the general rule for an arithmetic sequence comes down to the following. Now this may look weird, but trust me, it's actually very straightforward. I'm going to leave that there for you for a moment to copy down. The general rule for an arithmetic sequence. You want to get any term, the 600th term, the billionth term, the 471st term, it does not matter. If you have the general rule of the arithmetic sequence, you can get it. Every single arithmetic sequence follows this formula, where A sub 1 is your first term, and D is your common difference. Whether it be a positive number or a negative number does not matter. It's your common difference. For the example that we just did, our common difference was 3. So you would have D equals 3. So actually, let me do that example. The example that we literally just did was 5, 8, 11, 14, 17, dot, 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 dot. Yeah, cool. Well, my first term, my A sub 1 is 5. My first term is indeed 5. And my common difference is 3. Those are the two numbers that you guys gave me. I said, hey, give me a single digit number. You said 5. I made that my first term. I said, hey, give me another single digit number. You told me 3. I made that my common difference. All I would have to do is plug those two numbers into that formula. A sub n equals my first term plus parentheses n minus 1 times 3, because that would be my common difference. If I were to take that 3 and distribute that sucker, I can then simplify this thing down to what I got on the previous page. I'd have to distribute that 3 properly and ultimately get 3n plus 2, which is the general rule that I wrote down on the previous page. With that formula, I can get any term in that sequence. Does not matter. kind of look like to you? Like when you see 3n plus 2, what does that kind of remind you of? Maybe something from, I don't know, Algebra 1. Or pre-algebra. What does that remind you of? And mind you, I did not teach any of you Algebra 1, clearly. I did not teach any of you pre-algebra. So I have no idea how much you actually remember from that time in your lives. 3 times a variable plus 2. Ugh. I'll tell you what it should remind you of. What it should remind you of is slope-intercept form. mx plus b. Your slope times your variable plus your y-intercept. That's what it should remind you of. I say should because, again, I have absolutely no idea. I have absolutely no idea what you remember. Oh, check this out. Sorry, I just got an email about those things in the hallway. I'm gonna read this to you guys. You ready? Somebody emailed the principal and said, Pat, I just wanted you to be aware that the C-wing chiller, whatever the heck that is, had a major board malfunction last week. We overnighted a new controller, which also would up being defective from the factory. Oh, which also wound up being defective from the factory. We overnighted a controller once again, and it turns out their entire inventory of these controllers were defective from the factory. We have installed 4 temporary air conditioning units upstairs in the halls. For now, that should trickle into the classrooms and down the stairwells. If you would please advise the teachers to keep windows shut and doors open to the hall for a few to keep humidity levels at bay, the classroom units will continuously circulate and put the cooler air in from the halls. Okay, I'm gonna do that actually. Here, someone get the window. I'm gonna get the door. What a day. What a day. It's like, you gotta be kidding me, man. So I'll tell you just a quick story about the heat. Remember when we all shut down last year? Do you know what they did to the most of the school during that time? They desanitized all the classrooms and locked them all up. And there was 0 air circulating through C-Wing last year. To the point where when I came back, most of my handheld calculators, the batteries had bled out into the backs of the calculators. I lost 5 or 6 good calculators because of, like, the stuff that leaks out of a battery, whatever it is. The what? Yeah. I think it's called, yeah. But it's because they didn't put the heat on. So when you don't put the heat on for like a full-on year, no, I'm sorry, not the heat, the air conditioning. When you don't put the air conditioning on for a full-on year, and you're like, oh, I wonder why C-Wing is so hot. Gotta be kidding me. Sorry, I shouldn't complain, but I probably will. What a world. Anyway, back to this. Okay. I have a couple examples that I'm going to walk you through. I have a couple examples that I want to walk you through to kind of like wrap up today. These are 2 examples that I definitely want to do with you. Because again, this is an introduction. I'm going to split this in half. And I got these 2 examples. Oh, I got the hiccups too. That feels good. -1, 3, 7, 11. ... And I say find the general rule. That's my directions on that particular problem. And when I say find the general rule, I mean literally what we just did. But then I have an extra challenge for you. My extra challenge is this. D equals -2. Someone give me a 2-digit number, like a ridiculous 2-digit number.
99.
Okay, let's do 99. Let's do 99. I think 99 would actually work out really well. Yep, there it is. A sub 99 equals negative 187. You asked for it. That's a 99. So here's the thing now. You, at this point, oh, sweet. Joe in the chat also said 99. That's awesome. Good job, Joe. He put a sad face before when I didn't pick his number. I hope he puts a happy face now. We'll see if he does. I'll let you know. Here, hold on. I'll show you. Here. You can see right there. You put a sad face. Wait, where is it? Right. It's not focusing. Oh, he did put a happy face, though. Can I zoom in on that? Hold on. Hopefully it'll focus. There it is. There's the 99, he said. What inception. Anyway, back to this. So let me walk you through what you can do for the first example, and then I'll walk you through that ridiculous example. First, what's my common difference? 4. What's my first term? Negative 1. Those are the only two things you need in order to get towards the answer. It's a puzzle. Do you have the pieces to complete it? This one? Yes, you do. You have the pieces to complete it. You just need the common difference and the first term. You have it. Yes. So once you have those two things, once you have those two components, all you have to do is plug them into the formula and simplify. All you have to do is plug them into the formula and simplify. So I'm going to take that 4, and I'm going to distribute that sucker. It's going to give me negative 1 plus 4n minus 4. Combine like terms, and you get a general rule of 4n minus 5. This will get you any term in that sequence. For example, the 5th term, I'm going to point my red colored pencil there. The 5th term should be a 15, and it is a 15. And if you plug a 5 into the formula, you'll get 20 minus 5, which is 15. It works. It absolutely works. The problem that you run into, and like I said, this will be the last main problem we do today, but the problem that you run into is with the next example. What do you need in order to proceed? What do you need in order to get this problem done? I need the first term. Clearly, I did not give you the first term. I gave you the 99th term. Oh, you could do this if you wanted to. Check this out. You could do this, although what I'm about to show you is not practical. It's not practical, what I'm about to show you. Check this out. This is not practical. You can't be like, okay, negative 187 is the 99th term. The common difference is minus 2, which means it goes minus 2, minus 2, minus 2 every single time down the sequence. That's what it does. You can't then work your way backwards like this. I mean, technically you can. Plus 2. That's the 98th term. 97th, 96th, 95th, 94th, 93rd, 92nd, 90th. You could do that if you wanted to. You could. But it's tedious and it's not practical. I wouldn't recommend it. I wouldn't recommend it. Instead, I would recommend doing this. A sub n equals the first term plus parentheses n minus 1 times d. I don't know what the first term is, but I do know what the 99th term is. I'm going to plug a 99. Look what I have written there. I'm going to plug a 99 in for n. I still don't know what the first term is. But since I'm plugging in a 99 for that n, I can plug a 99 in for the other n as well. And I know what the common difference is. The common difference is a -2. I know what the 99th term is. They gave me the 99th term. I know what that result is. It's a -187. I'm going to go to my calculator real quick. And I know that that's -196. What I did right here was I did a 99 minus 1 times -2. And I got -196. If you work this problem out as I have done, then in a few short lines of work, you can easily figure out that the first term should be 9. The first term should be a positive 9. That's what it is. Now, that's not my final answer, because I still need to find the general rule. But that's what you could do. Utilize that formula. It's the same formula that we've been doing. I've only taught you one formula today. But it's the same formula that we're using over and over again in order to manipulate these arithmetic sequences. I mean, like I said, if you wanted to, here, check this out. I'm going to actually give it a shot. I'll start with -187, and I'll add 2. 8, 9, 7, 6, 5, 4, 3, 2, 1, 0, 9, 8, 7, 6, 5, 4, 3, 2, 1, 80, 9, 8, 7, 6, 5, 4, 3, 2, 1, 70, 9, 8, 7, 6, 5, 4, 3, 2, 1, 60, 9, 8, 7, 5, 6, 5, 2, 1, I already lost count, 50. I'm pretty sure I'm going to mess up. 9, 8, 7, 5, 6, 5, 4, 3, 2, 1, 40, I think. Probably wrong on this one. 9, 8, 7, 5, 6, 5, 4, 3, 2, 1, 30. 9, 8, 7, 5, 6, 5, 4, 2, 1, 30? I don't know what number I'm on. 9, 8, 7, 5, 6, 5, 3, 2, 1. That might be 10. 9, 8, 7, 5, 4, 3. Yeah, I was off by 1. I'm trying to do it quick. Like, why would I waste my time doing that when I could literally just jump straight to the answer here? But then if I want the general rule, I know what my first term is now. I can just plug that information in where it's supposed to go, like I've done before, and I could jump straight to my answer. Just be careful when you are distributing a -2. Be very careful when you are distributing a -2. Now, like I said, this is an introduction, introducing you to what a sequence is, defining an arithmetic sequence, and showing you the formula defining the general rule of an arithmetic sequence. How to use it, how to manipulate it, how to use it to your advantage so you tried to do in the calculator, which was clearly wrong. But what I have written on the paper is 100% correct. I still have to show you next class how to do a geometric sequence. They're kind of nice. I like them. And then after that, I'm going to be able to show you on Friday what Carl Gauss did when he was an adult and the formulas that he was able to devise. 2 reminders. One for the chat. If you have not left a comment, please make sure that you do so. But other reminder for all of you. There is the major on edge elastic, on rationals. It is due Friday. Like I said, a couple of you have already done it. Good for you, but it is not due until Friday. Email me if you have any questions in regards to that edge elastic major. After Friday at 2 o'clock, I will, well, probably Friday. I don't know what time I'll actually do it. Maybe I'll do it Saturday or Sunday, but I will update those grades for Google Classroom so you can see exactly what number you got. In the meantime, the bell is still 2 minutes away, so I'm going to leave the chat open for just a very brief few more moments so people can put in those comments if need be. Otherwise, I will be signing off. Yeah, you got time. Man, Wednesdays are like a half day for you guys, but like they drag. My word. Also, the heat does not help. Question, has it gotten any better with the door open? Okay, maybe. I mean, you are wearing like a hooded jacket. I gotcha. All right, I'm going to get off the live chat. They should have had enough time to add their comments. There they go.